Chapter 2, Heating Efficiency. This chapter covers the various ways heating systems lose heat and defines the different efficiency terms used to describe heating system operation. The purpose of an oil-powered heating system is to release the energy contained in the fuel and convert that energy into useful heat in the building. No heating system can operate without some heat losses. Part of the energy contained in the fuel is lost before it can be delivered as useful heat to the radiators or registers. The efficiency of the heating system is simply the percentage of the fuel's energy that is delivered to the living space of the building. The lower the heat losses, the higher the system's efficiency. Heating systems lose energy in many ways, starting when the pump delivers the fuel to the burner up until the heat reaches the living area. Some of these depend on the design of the burner, furnace, boiler, or water heater, the venting system, and distribution system. Additionally, how the system is installed, adjusted, and maintained will also affect the efficiency. Finally, how well the building envelope is sealed and insulated determines how long the heat created by the heating system stays in the building. Impacts on efficiency. The actual efficiency of the oil system is affected by the following factors: the efficiency of the burner boiler or burner furnace, the chimney design and upgrades, installation practices including boiler or furnace sizing, boiler water or furnace air operating temperatures, piping or ducting design, sealing and insulation, and the source of combustion air. Efficiency is also impacted by service procedures, such as barometric damper settings, sealing air leaks into the boiler or furnace, burner adjustment, excess air and smoke, cleaning boiler or furnace heat transfer surfaces as needed, and proper nozzle sizing. Other factors that affect efficiency are the building design and construction, the location of the unit in the building, chimney draft zoning of the distribution system, and the domestic water heating system. Types of heating system heat loss. Heating systems lose heat in 5 ways. On-cycle flue heat losses, that is, losses that occur while the burner is running. Off-cycle heat losses that occur when the burner is off. Jacket heat losses from the boiler or furnace and water heater casing. Distribution losses from the steam or hot water pipes and air ducts. And infiltration heat losses from cold outdoor air being drawn into the building as a result of the operation of the furnace or boiler. The flue heat loss during burner operation is called on-cycle losses. One of the largest heat losses in a building is the heat that goes up the flue while the burner is running. The oil flame produces hot gases that pass through the heat exchanger and up the chimney. Most of the heat contained in these gases is transferred to the heating system water or air in the heat exchanger. It is then transferred to the living space. Combustion efficiency tests measure these losses. Flue losses that occur when the burner is running are divided into 2 parts: water vapor heat loss and excess air, or we call sensible heat loss. This is the heat carried out of the building with the hot exhaust gases. On-cycle heat losses for oil heating units vary depending on heating equipment design and servicing. Studies show the average on-cycle losses as measured by CO2 or O2 and net stack temperature for burners installed before the 1980s of about 28%, with a typical range of 20 to 30% of the total heat content of the fuel. This can be separated into 8% from water vapor loss and about 20% from excess air heat loss. The performance of older systems could be improved significantly by replacing the burner with a new flame retention model. However, the most effective way to reduce excess air heat losses is with a new boiler or furnace. New appliances operate very efficiently with on-cycle losses ranging from 9 to 14%. Combustion air normally enters the burner or basement air temperature, which is usually about 63 degrees. The exhaust gases at the breech are normally between 350 and 600 degrees. The heat in these gases go up the chimney are heat losses. Some loss is unavoidable, but heat loss can be reduced by better burner air adjustment, clean heat exchanger surfaces, or equipment replacement. New equipment uses much less combustion air, and some units do not need a draft regulator, hence less heat flow up the flue. Let's first look at water vapor loss. The water vapor loss, or latent heat loss, is covered in Chapter 1. It is fixed and cannot be altered except through the use of condensing furnaces or boilers. That will be covered in Chapter 4. The only way to reclaim this energy is to lower the combustion gas temperature to a point where the water condenses, turns from steam into water, thereby releasing the latent heat. This should only be done in specifically designed condensing boilers and furnaces. Excess air, or sensible heat loss, is the heat is also called chimney loss and is the amount of energy that leaves the building along with the combustion gases. The chimney must be heated in order for it to operate. The larger the temperature difference between the combustion gases and the outdoor temperature, the stronger the draft. Therefore, the chimney must be heated to create the draft needed to draw the gases out of the building. The combustion gases that must be removed from the building include carbon monoxide, smoke, sulfuric oxides, nitrous oxides, steam, and carbon dioxide. The size of this heat loss varies from unit to unit and is determined by the volume of gases that must be removed. The more gases, the lower the efficiency. Off-cycle heat losses, or we're also called idle losses, occur when the burner is not running. Oil burners do not operate continuously. They cycle on and off in response to demand. Because most boilers and furnaces are oversized, the typical residential or light commercial burner operates between 15 and 20% of the time during the heating season, less than 800 hours a year. Idle losses occur because chimneys continue to draft even when the burner is not operating. Whenever the air inside the chimney is hotter than the air outside the chimney, it creates a negative draft. When the burner is off, the draft pulls warm air into the burner air intake, across the hot heat exchanger, and up the chimney. It also draws warm air from the room into the draft regulator and up the chimney. If the boiler or furnace has any air leaks, air will then be pulled into the room through these leaks and also go through the heat exchanger and up the chimney. The air that goes through the heat exchanger is a particular problem. The room temperature air will be heated as it goes through the heat exchanger. Remember, heat goes from hot to cold, and in the winter, the heat exchanger will be warmer than the room it is in. This heated air flowing up the chimney keeps the chimney warm, which keeps the heat flowing up the chimney. The best way to demonstrate this loss to yourself and your customer is to insert a thermometer in the flue pipe after the unit has shut down. Watch how long it takes for the temperature to drop to room temperature. The whole time it stays high, energy is being taken from the heating system and the building. The main factors contributing to idle losses are the burner design. A retention head allows less airflow through it than an old non-retention head burner. Okay. The heat exchanger design. The tighter the heat exchanger passes and the higher the draft drop through the heat exchanger, the more it resists airflow. Heat storage capacity of the appliance. High mass units retain heat longer and have greater off-cycle losses. Chimney height and construction materials. The operating temperature of the boiler, that is the water temperature, or the furnace, the air temperature. Air leaks into the appliances. Frequency and length of off and on cycles. The shorter the cycles, the greater the losses. Heating system sizing is an important factor that affects on-off cycling and heat loss. Oversized heating units will have longer off periods and off-cycle losses will increase. A heating unit that is closely matched in size to the building's heating requirements will provide the lowest off-cycle heat loss and highest efficiency. It might be possible to underfire of an old oversized furnace or boiler to match the firing rate to the load. There are 3 times when underfiring is a bad idea. Never underfire a steam boiler. Never underfire a boiler with a tankless coil because the customer will run out of hot water. Or any unit where the net stack temperature drops below 350 degrees Fahrenheit. Sealing up air leaks into the heat exchanger will lower idle losses as well as lowering the operating temperature of the unit. Restriction of off-cycle airflow by the burner head can reduce heat losses. Generally, older burners were designed with open combustion heads that provided very little resistance to off-cycle airflow. In contrast, the restricted air passages in a new high-speed flame retention burner reduce off-cycle airflow and thereby reduce heat losses. New oil vent dampers are a way to reduce off-cycle losses on older boilers and furnaces. They are a motorized damper installed in the vent pipe between the draft regulator and the chimney. They must be installed with a blocked vent safety switch to keep the burner from running if the damper fails to open on a call for heat. Most new equipment uses low-mass ceramic fiber combustion chambers that store less heat than the old high-density fire brick materials used in older equipment. Thus, they will have lower off-cycle losses. Small low-mass boilers or furnaces store less heat than their older, heavier counterparts and will save energy because they have lower off-cycle losses. Jacket losses is the heat loss through the jacket or casing of the appliance. It reduces the amount of heat delivered to the building and lowers system efficiency. Jacket losses are affected by the location of the appliance. If the unit is located in the closet off the kitchen, then most of the losses go into the house. If the unit is located outdoors or in a garage, the losses are very real and the units must be well insulated to reduce jacket losses to acceptable levels. Based upon Brookhaven National Lab testing, jacket losses from appliances can vary from less than 1% to more than 10%. This loss is highest while the burner is firing. Typical flame temperatures of approximately 2,000 degrees Fahrenheit drive heat through the chamber wall and then through the jacket. Dry base boilers that do not have water surrounding the combustion area tend to have higher jacket losses than wet base boilers where the water-backed heat exchanger extends around the combustion area to the floor. One way to capture some of the jacket losses from a boiler or furnace installed in a basement is to seal up the air leaks into the basement and to insulate the basement walls down to below the frost line. This results in the jacket losses heating the basement and the basement ceiling, which of course is the floor for the first floor. Distribution system losses from pipes and ducts. The heat from a central boiler or furnace is transported to the home through pipes and air ducts. Heat loss that occurs between the heating unit and the living space causes system inefficiency. The level of heat loss depends on how and where the pipes and ducts are installed, the size of the distribution system, and the amount of thermal insulation. Uninsulated pipes and ducts that run through unheated areas have very large heat losses. A properly designed and installed heat distribution system can operate with very low duct or pipe losses. Heat losses from steam or water pipes and air ducts are not measured for the government AFUE annual fuel utilization efficiency rating and vary widely from building to building. The biggest distribution losses come from leaky ducts. As you can see from this picture, there are lots of places where the ducts can leak. Everywhere there's a joint between two different pieces is a potential leak. We will cover this in more detail later in the program. Outdoor air infiltration. All fuel burning heating units consume air for combustion and for off-cycle draft. The air that passes out of the building through the chimney must be replaced by cold air drawn into the building. When the cold air is brought into the building, it goes through the living space and is heated. The energy required to heat the cold air is infiltration loss. In most cases, a burner operating in an unconfined space of a conventional building will receive adequate combustion air supply from air leaks into the building. But if the burner is located in a confined space, such as a furnace or boiler room, the enclosure must have one permanent opening into the rest of the building near the top and one near the bottom of the enclosure to let in combustion and draft relief air. The burner is located in tightly constructed or properly sealed building. Outside air should be supplied for combustion. This slide shows various ways to bring outside combustion air to the burner. The size of air infiltration heat loss depends upon the on-cycle airflow through the heating unit and the draft regulator, as well as installation factors such as the location of the heating unit within the building. Air infiltration loss is greatest for heating appliances that operate with large quantities of excess combustion air or units that have large off-cycle air flows. Efficient units will operate with low air infiltration losses. The best solution for air infiltration loss is isolated combustion, whereby outdoor air is piped directly to the burner air intake. Infiltration losses from new units with isolated combustion air that require no draft regulator can be almost zero. There are many different types of heating systems and many different definitions for efficiency. Fuel conversion efficiency is the percentage of the fuel that is converted to heat in the flame. If the burner is set for zero smoke, then all the fuel has been burned and the fuel conversion efficiency is almost 100%. There's no unburned hydrocarbons left in the combustion gases. Combustion efficiency or steady state efficiency includes the fuel conversion efficiency, the amount of excess air used, and the efficiency of the heat exchanger. This is the test technicians do in the field. Combustion efficiency only describes on-cycle losses. It does not include jacket losses, off-cycle losses, distribution, or outdoor air infiltration losses. So combustion efficiency is a great service tool, but it's not a very good sales tool, and it should not be the end of the analysis. There are still many old, oversized boilers with 1970 flame retention burners. What we used to do in the 70s was, with careful nozzle sizing and adjustment, the CO2 on these units can be as high as 10%. Lowering the firing rate by putting a tiny fire in that big pile of cast iron can probably get the stack temperatures down to about 400 degrees. This works out to 81.5 combustion efficiency. However, the jacket losses for that unit could be as high as 8%, the off-cycle losses at least 15%, and the infiltration losses through that 8-inch draft regulator and the leaks between the sections is about 10%. The true efficiency is 33% lower than the combustion efficiency indicated. Telling the customer they can save money with the new $9,000 boiler that could improve combustion efficiency from 81.5 all the way up to 87 is not very compelling. Obviously, a way to describe all these other losses is needed to demonstrate to customers how much better the new equipment is than the old equipment. Annual Fuel Utilization Efficiency, or AFUE. This is the U.S. government Department of Energy's attempt to provide a rating for boilers and furnaces. It is based upon standardized testing and calculation procedures developed by the DOE in the late 80s. Manufacturers must perform these tests on every model of residential boiler or furnace they sell. These AFUE results are printed on a yellow label that must be affixed to the unit. They are also listed in several heating equipment directories. Unfortunately, equipment manufactured before 1985 does not have an AFUE rating and cannot be compared to today's equipment without further analysis. The objective of AFUE labeling program is to supply consistent efficiency information to help consumers select and install high efficiency equipment. While there are some serious flaws in this procedure, it is the only consistent information available for comparing units. AFUE indicates the efficiency of the burner-boiler or burner-furnace combination for a set of operating conditions. It is not intended to measure heating system efficiency, which includes heat losses that vary from building to building. The test procedure approximates on-cycle heat loss and cool-down characteristics, and then calculates off-cycle losses and infiltration losses for standard conditions. There are many real-world cases where off-cycle and infiltration losses are significantly different than those predicted by AFUE. Jacket losses are generally not included, even though they may be significant. AFUE is used to rate the overall efficiency of a new boiler or furnace over an average heating system for a typical operating conditions. While the AFUE test cannot and does not try to take all factors that determine efficiency into account, it does give us a way to compare the relative efficiencies of the average new furnace or standard space heating only boiler. AFUE is no help when evaluating the relative efficiencies of integrated space and water heating systems. AFUE's biggest drawback is that it's no help when determining the potential savings replacing a pre-1985 boiler or furnace with a new one. AFUE does not apply to water heaters that are used for space heating. It also does not describe the efficiency of a boiler that is also used to make domestic hot water. This brings us to heating system annual efficiency. This is the actual true efficiency of the whole system over the heating season. It is the difference between the number of BTUs the consumer bought and the number of BTUs they used to heat the building and domestic hot water. It involves all of the energy losses and system interactions measured over the course of a whole year. It is the function of the gallons of oil used, the temperature of the outside air, solar gain, exposure to wind, the temperature inside the building, the number of occupants and their lifestyle, as well as the amount and temperature of the domestic hot water they used. Unfortunately, there is no standard way to measure the heating system efficiency, and each building has a different efficiency. The annual heating efficiency cannot be measured on a service call. We don't know how to measure it, but we do know how to affect it. Here are some of the factors that cause heating system efficiency to vary from AFUE. First, the location of the boiler or furnace. Does the jacket and distribution losses help heat the living space, or don't they? Chimney draft. The chimney height, what the chimney is made of, and the air temperature all affect on-cycle and off-cycle losses from the chimney. The source of combustion and draft relief air. Burner design and operating pressure. Boiler and furnace sizing and firing rate relative to the heat load, the zoning of the distribution system, pipe or duct design and installation, the source and consumption of domestic hot water, the mass of the boiler or furnace control system. It's also affected by air leaks into the boiler, the insulation of the building envelope, and the electric consumption of the heating system. Highway mileage versus city mileage. For years, technicians have measured steady-state combustion efficiency and used that number to characterize the heating system efficiency. It's like using highway mileage for a car. If you think about it, with highway mileage, your engine is warmed up and you're cruising along the interstate in high gear. You're getting your very best mileage. Heating system annual efficiency is more like city mileage, with stop-and-go traffic and idling at red lights. The problem is that when trying to sell customers new equipment by looking at the highway mileage for the old unit and the city mileage for the new unit, that is the AFUE or heating system efficiency, the savings potential is underestimated. The old steady-state efficiency, as we said, could be 81.5, and the new AFUE is 87. For a savings of 5.5%, when in fact the actual savings for that unit can be as much as 38.5%, a much different number when calculating payback. In order to convince customers to invest in new equipment, technicians must understand annual heating system efficiency, city mileage, and all the factors that go into that number. The NORA Fuel Savings Analysis Calculator is a step toward really understanding the true efficiency of the heating system. This was developed by the New York State Energy Research and Development Authority, Brookhaven National Labs, and NORA as a way to predict the actual savings for replacing an old boiler or furnace with a new one. It is called the Fuel Savings Analysis Calculator. This calculator is always being improved, so make sure you use the latest version. To find it, go to noraweb.org and click on the FSA calculator icon.